Okay, hello everyone, I'm Salar and we are in part 22 from our tutorial to writing a real-time operating system. In previous part, I talked about instruction encoding, ARM instruction, thumb instruction, and thumb version 2 instruction. Okay, but in this part, I want to talk about some assembly programming points, but before that, turn on an LED. Okay, in this part, I want to turn on an LED with assembly instructions in my board. And I want to talk about some instructions, for example, compare instructions, test instruction, and some about branch and branch conditional instruction. Okay, but before to turn on an LED on my board, let's talk about pseudo instructions. What's a pseudo instruction? As the name implies, it's not a real instruction. What does mean it's not a real instruction? Means that your instruction does not encode it just to one instruction. Okay, and why we need to pseudo instructions? We can write or code without pseudo instructions, but pseudo instructions can make our work in programming easier. Okay, let's give you an example. For example, LDR and register an equal sign. Its equal sign is so important. And constant number. The maximum range of this constant number is 32 bits. Okay, for example, 0x 1 2 3 4 5 6 7 8. With this pseudo instruction, I can load this value in a register just by one instruction. Okay, just by one pseudo instruction. For example, I can write in my code, for example, LDR2 R0 equal 0x 1 2 3 4 5 6 7 8. And in this way I can write a value in register R0, 32-bit value, instead of, for example, write move W a 16-bit and move T upper part of your register. Okay, in this way you can write with two register. This register is for thumb version 2, but in this register I can write a value in register R0 just by one instruction in my code. Okay, let's give you an example in Eclipse. Okay, as you can see, I have just one instruction, and with this instruction I can load my register R0 with a 32-bit number. Okay, let's debug this code and see the result. Now I'm in debug perspective and I'm in line 4, first line from my main block. Okay, and if I press F6 or run next, now in register R0 I have my value. Okay, just by one instruction, pseudo instruction in my code, I can load my register with a 32-bit number. Okay, but why your assembler and your compiler or tools can't do this work? Let's see object code with object dump and see what's under the hood. First, let's minimize that and go to Eclipse workspace, my project directory, and here main.o, object of main.s, object file of main.s. Open terminal and run arm object dump -d and main.o. Okay, as you can see, here is my code. Okay, it's my first instruction, load instruction converted to a load. Okay, LDR to LDR, but R0 PC and offset load instruction, okay, with PC based, okay. And here, after of my code, just after of my code, here is branch instruction. Just after of my code, I have my constant value in flash memory close to my code, okay. Here is my code, just after my code, near to my code, close to my code. So I can have access to this value in flash memory with address of PC and an offset, because my number is close to my code, okay. So PC, as I said, PC keeps the address of next instruction. For example, when you want to run this instruction, the address of the value of PC is 0. When you want to run this instruction, the value of PC is 2. But 0, 2, and 4, these are relative number, and your linker in link stage relocate this address and convert this address to absolute address, okay. But in this time, in my object code, these addresses are relative address. But anyway, I have a load instruction, real load instruction, instead of my pseudo instruction, but using PC and an offset. How your assembler can find this offset, okay, can find this offset with this formula. Let's write the formula. The formula is align for of PC address, okay. What's align for of PC address? PC minus PC moved by 4, okay. It can align your PC address to a word align, okay. Align by 4 plus 4. Why plus 4? Because this number is related to pipeline structure of your processor. If you want to what's pipeline in processor and in architectures and in microarchitectures, study the book, the computer organization book by David Patterson and John Hennessy. I talked about that in previous part, okay. This number is related to a structure of your processor because your processor is a pipeline processor, okay. And plus offset equal to address of your constant number, okay. So for example, here is PC address, here is offset, and here is address of constant, okay. Let's do, for example, solve this formula for this part of code, okay. PC, in this time when you want to run this code, PC is 0, okay, offset is 0, and address is 4. Let's run that. For example, PC is 0, aligned by 4 is 0, plus 4, and plus offset is 0. The address of my constant is 4, okay. The address of my constant is 4. Let's to change my code and make it more complicated. First, stop debugging and add, for example, some instruction in my code. For example, no operation. No operation is an instruction that do nothing, okay. For example, add some no operation in my code for 3, 4, 5, okay. Let's do make my project, and another time see the text section. Another time, here is my code, but in this time PC address is 2, offset is 12, and the address of your constant number in your flash memory, the relative address is 10. Here is a hexadecimal number, okay. Let's do solve the equation for these values. As I said, PC address in this time is 2, but aligned by 4 is 0, okay? 0 plus 4 plus offset is 12. The result is 16. Here is a decimal number, but the hexadecimal form 10. As you can see, the address of my constant value is 10. But as you can see, this value, the 32-bit value, decoded to an instruction, but because it's not a real instruction, it's not a real encoded instruction, just a constant number, here is a dummy value, okay? It's not important what's here, because here is a constant number. It's not an instruction. It's not an instruction. But before, as you can see, I've written here, for example, as you can see, put constant number in flash, put constant number in flash, how your assembler can create and can do this instruction. Put constant value in your flash in the end of your code, after of your code, with LDR instruction and PC address, load the constant value to RD register, okay? But for a smaller constant, your assembler converted your instruction to move instruction. For example, for a bigger constant, for example, a 32-bit number, your assembler converted your instruction to a load instruction with PC address and an offset, and put your value after of your code, okay? Just after of your code. Okay, so another important thing in programming is literal pool. What's a literal pool? A pool of your literal, as the name implies. But create a lookup table for constant value with a literal pool and these directives, okay? You can create a lookup table for your constant value, and you can write your constant value in your flash memory, in a non-volatile memory. For example, with Word, you can write a 4 byte. With Half-Word, you can write a 2 byte. With byte, you can write just 1 byte. With ASCIIs, you can write a string that terminated by null, okay? Terminated by null. Null is a 0, okay? And quad is a 8-byte data, okay? But let's do an example and simple and see what's a literal pool in programming. Okay, here I have a code part and I want to use this directive to create a literal pool. For example, as you can see, I've added .word after of my code, okay? After of my code. And in this way, you can write this value in your flash memory with .word, okay? .word and my constant data, a 4-byte data. Another time, .word after this constant value in memory, this value, okay? And after that, and .ASCIIs and a string, okay? But I've added 2 labels in my code, my number and my text. As you know, a label is an address, okay? A label will convert it in your assembly code to an address. For example, here is my number address of this byte, okay? First byte of this 4 byte, okay? My number is address of first byte of this 4 bytes. Or for example, my text is address of first byte of this string. So how can I load these values in my register file, okay? First, use a pseudo instruction, but in this time, write your address here. For example, my number. And after that, with this address, you can load the value in register are 1. Okay, let's run this code and debug that to see the result. Okay, here is my code, and in line 1 I want to write this address to register R1 with this pseudo instruction. Okay, run that. Now the value of R1 is address in my flash memory. Okay, here is address in my flash memory in my microcontroller. But let's use this address, copy that, and open your memory viewer. Okay, here is my memory viewer, and paste this address here. Control V and OK. Now I have my value here, 78, 56, 34, and 12. Here, this is my value, little endian. Okay, it's written to my flash memory. Okay, now with this address that is in R0, I can load this value in register R1. Another time, press next. Now the value of register R1 is 1, 2, 3, 4, 5, 6, 7, 8. Okay, and after that I want to load this value in my register, but I just have address of this value. But first address of this constant is address of this value plus 4, because here is 4 bytes. So I can use offset 4. Okay, another time run that, and another time next. Now in register R3 I have let's see, in register R3 in register R3 I have just value of my text. Okay, but in register R2 I have this value, because this is address of this value plus 4 is address of this value. In register R2 I have my constant number 8, 7, 6, 5, 4, 3, 2, 1. But how can I see this value in my memory? As I said, address of my text in this time is register R3. Okay, copy content of register R3, copy that, and open memory browser. Okay, in this time memory browser, not your memory. Okay, memory browser, paste your address here and press enter. Now here in my memory I have hello world. With memory browser you can see the character value in your memory. Okay, but because here I have a hello world, a meaningful characters, I have hello world here, but other characters are just byte numbers, not meaningful characters. But I have hello world in this address, okay, in my text. So in this way I can create a lookup table like here and use it in my programming, okay, in my assembly programming, and add some constant values in my assembly program. Okay, let's do stop debugging and back to but before to back to our slides, what's under the hood in this time, okay, and how your assembler can find the address of my number, for example. Okay, how your assembler and your tools can do this. Let's delete this part and this part, and another time build my project. Okay, here is my code, and I want to see another time my object code. Okay, another time run object dump and see your code. As you can see, here is my code. Another time with LDR, PC, and an offset, you can find the address of this constant. But what's the address of this constant in my flash memory is 4. But your assembler saved your address in another 4 bytes, in byte 8. Okay, address of 4 here is value of this word in your memory. Okay, so another time let's do that formula for this instruction. My PC is 0, my PC address is 0, and my offset is 4. Okay, another time do this formula. PC value is 0, the aligned for is 0 plus 4, another time plus 4, your offset is 8. Okay, so your processor will load the value of address 8. Here the value is 4 to register R0. So in register R0 you can have the address of this constant number. Okay, with literal pool your assembler will add the address of your constant number in your flash memory. Okay, and with this instruction you can have access to this address, and with this address in register R0 you can have access to this value. Okay, in this way you can use literal pool in your assembly programming. Here is what is under the hood in your assembler and in your processor. Okay, back to our slides. It's literal pool, but let's do turn on an LED on my board. Okay, turn on an LED on my board. I said in previous parts in C programming and turning on an LED on my board. If you want to turn on an LED, first you need to enable the clock of GPIO after the with this address and with this value. Okay, enable the clock of GPIO. After that, make your pin as the output with GPIO model register, and after that write the value 1 in your register, in your pin. Okay, and turn on an LED. So sorry, how can I write this value in this address in assembly programming? Let's give you an example. As you can see, with a pseudo instruction I can write the address of my register in address of my peripheral register in R0. Okay, after that load register 1 with number 1, bit 1. Okay, and after that shift register R1 8 times. Okay, logical shift left. Okay, you can instead of these two instruction write this instruction LDR R1 equal to 0x100. Okay, in this way you can write this value. This value is this value. Okay, you can write this value in register R0, but I've written in this way to that I've given an example for left shift. Okay, to find what's left shift. It's an sample. Okay, so with this code, first you write 1 in register R1 and shift it 8 times. So you have this value 1 shifted 8 times in register R1. After that, store the value of register R1 to address of R0. Okay, to this address. In this way you can write a value in a register and in your peripheral register. But let's do this example in Eclipse and turn on an LED on my board. Okay, here is my code. Write value in register AHB1ENR, write to register motor GPIOI motor register, and write to ODR register. Okay, to turn on an LED on my board. But as you can see, to write in AHB1ENR, I have a load instruction. Okay, it's a recommendation from datasheet of my microcontroller to, after writing a value in RCC register, one time read the value of your register to make sure that your value has been written. Okay, here is for that. But you don't need this load instruction in other register writing. Okay, build my code and run debug and see the result. Okay, here is my code. I'm in line 4, first line, and here is my registers. For example, RCCAHB1ENR, where is that? Here. And I want to write to this register GPIOI enable. Okay, first to run my code and store this value in this address. Run to line 8. Now here is highlighted. I written 1 in RCC register, and let's write in register motor, in GPIO, and register ODR. Another time, run to after of this instruction. Now the motor has been written. Okay, the motor value has been written, and another time run this value to turn on your LED. CODR register. Okay, now my LED is on in my board. Okay, very good. Let's just see the green LED on my board. Here, green LED is on in my board, and very good. With assembly programming, I can write in my preflop, in address of my preflop, and it's very good. Okay, so very nice. Stop debugging and back to the slides. Okay, back to the slides. In this way, I can turn on an LED on my board with assembly programming, and it's very good. But in next slide, what do we have? Branch instruction. We have used branch.l here in my code. But what's branch instruction and what's conditional branch instruction? A very good instruction to do a lot of things. But with simply branch instruction, branch and a label in your code. This label is offset from PC. Okay, has been converted to an offset from PC. Branch instruction. So you can branch from your PC, your next instruction, and with branch you can replace PC instruction, PC register with another address to jump to another part of your code. But how much is the range of this label? Okay, it's not important for you because you just write the label. You don't write a number. But for non-conditional branch, simply branch, just B. Here is non-conditional branch. For thumb version 1 is minus 2 kilobyte until 2 kilobyte to 2 kilobyte. For thumb version 2, because of 32 bits encoded instruction, you have much more bigger range, minus 16 megabyte to 16 megabyte before your PC instruction and after your PC instruction, PC value. Okay, and in conditional branch, I will talk about conditional branch in this part with thumb version 1 instruction from minus 252 to 258, and for thumb version 2 minus 1 megabyte to 1 megabyte. Okay, but it's not important for us because we use a label instead of an address, and your assembler can create this address for you. Okay, but before to talk about conditional branch, first to talk about compare instruction and test instructions. What's compare instructions? Compare instructions, for example, CMP, RN, RM, just like is just like to, sub S, flag updater, for example, RD, RN, RM. But in sub instruction, you write the result in register, but in compare instruction, you just do RN minus RM and update ASPR flags NZCV. Okay, this flag in APSR register. And another time compare with negative value. Okay, with negative value, it's just like add S, RD, RN, and RM. Update flagger. But in compare with negative value, you will not write, and your processor will not write the result in an instruction, in an register. Okay, in a register. Just do this arithmetic operation and update APSR flag, and you can have immediate instead of register. Okay, here is compare instructions. Compare instructions is one of flag updater. Okay, flag updater, like sub and S and add and S. Okay, but compare without S can update your flags. Another instructions is test and test equal. Test is just like and S, RD, RN, and RM, but will not write the result in destination register. Just add, bitwise add this to register and update just these flags N and Z, and will not update C and V because in logic instructions like AND, C, carry, and overflow has not been defined. Okay, and test equal is RN XOR RN. Okay, for example, with test instruction, if you AND your value, for example, in RN with this value and see the value in N, if N is 1, your number is a negative number. Okay, because in a negative number, two's complement number, most significant bit of your instruction is 1, and when you AND this value with this, the result value is 0x80000000. Okay, and your N bit, and the N bit in APSR register uh, will be 1. Okay, so with this value and your register, you can find, for example, it's an example, your number is negative or not. Okay, so after that, after compare and test instruction is another flag updater, because with this instruction you can update these flags. Okay, you can use conditional branch. Okay, conditional branch. What is conditional branch? A branch that related to a condition. Okay, for example, if you add a suffix after of your branch, for example, BNE, BEQ, you can create conditional branch instructions. All of suffixes are here. Okay, but before that, with conditional branch, how can I implement this code in C in assembly? Okay, how can I implement? If a variable equal to 1, do this part of your code. If variable is not equal to 1, do not run this part. It's simple if instruction. I can implement this code with conditional branch, but how? For example, assume here variable is in register R0 and this constant value 1 is in register R1. For example, assume that your variable is equal to 2. Okay, variable equal to 2. Let's do inspect this code and find what's this code. Here your variable is 2 and your value is 1. Okay, 2 and 1. In compare, I said it's just subtracting. Okay, Rn minus Rn. Okay, if you run this value, R0 is 2 and R1 is 1. R0 minus R1 equal to 1. So the value is not 0. So A, P, S, R, Z is 0. Okay, because the result of this arithmetic operation is not 0. So after that, branch not equal, BNE, branch if not equal. What means branch if 0 equal to 0. Okay, not equal, R0 and R1 is not equal, 0 bit in APSR is 0. So branch if Z is 0. Okay, so branch to this label if Z is 0 and Z is 0. So branch to this label and do not run this part of your code. Okay, variable is 2 and your code will branch over of your code, over of this part. Okay, because variable is 2 and do not and will not run your will not run the body of this if instruction, this if code. Okay, but another time, another scenario, assume that variable equal to 1, variable equal to 1 and your register 1, another time is 1, R0 minus R1 equal to 0. So A, P, S, R, Z equal to 1 because the result of update flagger instruction is 0. Okay, so here Z is 1. So branch if not branch if 0 equal to 0, but in this time 0 is 1, so your processor will not branch from this part and run this part. So when var is 1, you can run this part of your code. In this way, easily you can implement this C code in assembly with conditional branch. Very nice, very good. Okay, here is all suffixes. For example, EQ, branch, EQ, branch if equal, branch if Z equal to 1, Z set. Or for example, BMI, branch if n equal to n equal to 1. Or for example, LS, BLS, if C is clear, you don't have carry, and Z is 1. Okay, C is clear, lower or same, it's meaning. Okay, for unsigned value. Or for example, AL, branch in all conditions is just like simple branch. Okay, so in this way you can have conditional branch and use conditional branch for your work. If you want to have a homework, implement if and else, or for example a while instruction. Okay, a while instruction and with a condition. Okay, you can write all of this C syntaxes in assembly programming, and here is very good. I do a lot of works, we can do a lot of works with assembly programming, and it's very good. We know and now we know that what's under the hood in a C programming language. Okay, very good. Enough for today, enough for this part, and thank you very much to see me, and I will see you in the next part. Thank you very much.